We're in a real fight against microscopic enemies, and our best weapons are starting to fail. But what if the answer wasn't just another drug? What if it was a whole new kind of weapon, designed at the nanoscale and perfected inside a supercomputer, built to literally tear superbugs to pieces? So let's set the stage here, because this is important. We're talking about the huge global threat of multidrug-resistant bacteria. You probably heard of them as superbugs. And believe me, this is not some future sci-fi problem. It's happening in hospitals all over the world, right now. And the stakes? They could not be higher. The World Health Organization estimates that by 2050, these infections could kill 10 million people every single year. That's actually more than cancer causes today. So yeah, this is a fight we absolutely have to win. So what makes a superbug so, well, super? It all comes down to defense. These bacteria, especially a tough group called gram-negatives, have this outer membrane that's basically a suit of armor. It's incredibly hard to get through, which means our usual antibiotics just bounce right off. But what if you could just ignore the armor? Scientists have come up with a totally revolutionary solution that doesn't play by the old rules. It doesn't need to sneak inside the bacteria because it's designed to just obliterate that armor from the outside. So let's meet the hero of our story, the SNAPP. And as you can see, this is not your average molecule. It's a piece of nano-architecture, a tiny star-shaped polymer designed for one single purpose: to hunt down and kill superbugs. Okay, let's break down what we're looking at. At the very center, you've got a core. And then shooting out from that core, you have 16, or sometimes even 32, individual arms. Each arm is built from specific amino acids. You've got lysine, which has a positive charge, and valine, which repels water. It's this exact combo that gives the SNAPP its power to physically shred bacteria. And its attack plan is just brilliant. It's a 3-hit combo. First, those positive charges on the SNAPP's arms are drawn to the bacteria's negative membrane like a magnet, and they just start ripping it apart. Next, that breach causes total chaos inside the cell, messing up the ion balance and basically short-circuiting its power supply. And finally, all this physical damage actually triggers the bacteria's own self-destruct sequence. It's brutal and incredibly effective. Now here's the most important part. Because SNAPPs kill with brute physical force, bacteria just can't figure out how to evolve a defense against them. In the lab, scientists exposed superbugs to these things for over 600 generations, and the bacteria developed zero resistance. That is a game changer. So you've designed a nearly perfect weapon. What's the next step? The researchers asked a really cool question. Can we make it even deadlier? And the answer, it turns out, was to add a little something they called molecular grease. I mean, seriously, how do you improve on a weapon that bacteria can't even develop resistance to? Well, you make its attack even more efficient. You help it slip past the enemy's defenses even faster. And they did this with a process called lipidation. The idea is actually pretty simple, but it's genius. You just attach a fatty acid tail to the tip of each of those SNAPP arms. This molecular grease is meant to help the arms slide right into that fatty bacterial membrane, making it even better at piercing and destroying it. But of course, not just any tail will do, right? The scientists decided to try out 3 different options: a short one called C6, a medium one, C12, and a long one, C18. They knew that the length of this fatty chain could totally change how the SNAPP behaved. Now, instead of spending months, maybe even years in a lab making and testing each version, they turned to a supercomputer. They used something called molecular dynamics simulations, which is basically a virtual laboratory that lets you watch how molecules interact, atom by atom. And what they discovered was a classic Goldilocks story. One version was too short, one was way too long, but one was just right. Okay, so check this out. These are the results from those simulations, and you can see the difference right away. The C12 in the middle is doing exactly what it's supposed to. You can see its arms starting to punch right through that membrane. But look at the C18 on the right. It's just clumping up. It's not penetrating the surface at all. It's a completely different behavior. And this table just spells it out perfectly. The medium C12 tail, a huge success. It punched right through that membrane, no problem. But the long C18 tail was a complete failure. It didn't attack at all. It actually did something nobody expected. So what was going on? Well, the C12 tail was that perfect Goldilocks length.
It acted like grease, helping the arm get in and do its job. But the C18 tail was too greasy, too hydrophobic. It turns out the arms were more attracted to each other than to the bacteria. So instead of attacking, they just folded back and stuck to themselves, forming this useless little blob on the surface. And this chart is the proof. It shows how much energy it takes for each SNAP to get through the membrane. You can see that the bar for C12 is way lower than for the original SNAP, or that failed C18 version. It means it takes less energy for the C12 to do its job, which makes it a much more efficient killer.
So this brings us to the really big picture. This research isn't just about one incredible molecule. It's really signaling a fundamental change in how we're going to create the medicines of the future. What we're really looking at here is a new paradigm for discovering drugs. Think about it. Instead of years of trial and error in a lab, we can now design, test, and perfect these incredibly complex medicines inside a computer before a single one is ever actually made. And don't just take my word for it. The researchers themselves said that this work provides a framework, a blueprint really, for designing the next generation of weapons we desperately need to win the war on superbugs. So that leaves us with one last, really big question to think about. By combining what we know about biology with this massive computational power, are we walking into a new era where our best medicines are no longer found by chance, but are actually designed, atom by atom, right on a screen?